about boson sampling, which Yaron mentioned, or about quantum money. But I've actually already lectured about both of those here at Hebrew University. And, and besides, those are, results are already 2 or 3 years old. So instead, I'm going to lecture about something that's 12 years old. So this is this quantum lower bound for the collision problem. So, and there's actually a Hebrew University connection here. When I was a beginning grad student, in 2002, I visited Israel for the first time, and I gave one of the first talks of my life, actually, right here, about on this campus about the collision lower bound, which was sort of the most important thing that I did in grad school, I guess, and which I had just done a few months prior. And Avi Vigderson was there, and started, telling me to sort of get to the point faster, and I was like, well, that's really rude, but I didn't really understand Israelis yet, but I actually, took a liking to this country. I came back and spent the whole semester here, interacting with Dorit and with Mickey and so forth. Then, came back for many more visits. Even, married an Israeli woman, but that was later. Okay, so the plan of this talk is, I'll tell you sort of what is this collision lower bound, and then what's new in the last decade in terms of extending it and also sort of applying it to, in some crazy directions, including in cryptography and even in the black hole firewalls debate, and then, what are the big open problems that remain. So all right, the collision lower bound was a result that's in the framework of black box quantum computation. Okay, so what is black box quantum computation? Well, I don't mean this kind. Okay, so the kind of black box quantum computing that I mean is the kind where you're given a function, say f, and say from integers from 1 to n, to integers from 1 to m, and you're interested in determining some property of f. For example, in Shor's algorithm, you would like to know, is f periodic? Or, if so, what is its period? Okay, in the Grover problem, you'd like to know, sort of, is there, an x where f of x equals 1? Okay, so the crucial assumption is that you only get to learn about f by making queries to a black box that, reveals the value of f of x for a given x. Okay, now because this is quantum computing, you get to query the black box in a superposition of a whole bunch of different values. Okay, so you can feed it a state like this. X is an input, A is an answer register, W is just some workspace, some extra stuff. And, you'll get in superposition the f of x's sort of written into the answer register. Okay, and then in between two queries, you can apply an arbitrary unitary transformation that doesn't depend on f. Okay, so like this would be the reflection operation in Grover's algorithm, for example. Okay, and then you can make another query, another unitary, and so forth. And the question that interests us is, what is the complexity of, computing the thing that interests you, like, the period of the function or whatever. And the complexity just means what is the minimum number of queries to f, that are made by the optimal quantum algorithm. Okay, and a quantum algorithm that should succeed with high probability for every possible f. Okay, so, now, the reasons why we study this black box model is, first of all, it models very well how most of the quantum algorithms that we actually know work. Okay, so Shor's algorithm, at its core has this black box algorithm for, finding the period of a periodic function, right? Grover's algorithm, is in this model also. Okay, and, and other quantum algorithms as well. The other nice thing about this model is that we can actually understand it. With some effort, we can actually prove, that, here's like an algorithm, and this algorithm is the best possible. right? We don't have to assume that, that P is not equal to NP or anything of that kind, okay, in order to be able to prove, optimality of our algorithms. Okay, now, if F, if we assume that this function F, that you knew something about its structure, like that, F were described to you explicitly by a Boolean circuit, okay, then, there would always be the possibility, even classically, that some algorithm might be able to sort of go into F's internals and do something more clever, okay, than just, evaluating it as a black box. Right, and so then, in order to prove that, there's no fast algorithm to do something, you would indeed have to assume that, P is not equal to NP, right, probably just at the very least. Right, but in the black box model, we're just going to assume that, look, you have a subroutine that you can call, you can run it in quantum superposition and it computes F for you. Okay, but you don't know or the internals of this subroutine. Okay, or they're too complicated for you to understand. Okay, so that's the model. Okay. Okay, so so well-known examples, that I mentioned already. For Grover search, we know that square root of n queries to F are both necessary and sufficient. Okay, for finding like a marked input. Actually Grover's algorithm was proved to be optimal by Bennett, Bernstein, Broussard, and Vazirani before it was discovered to exist. Okay, so this square root of n is the tight answer. Okay, for finding whether F is periodic, actually what Shor showed is that even just a constant number of queries to F suffice. If you get to query F in superposition. If you have to query F classically, well then you need like square root of n queries. Okay. Okay, so the problem that we're going to be interested in is a problem that, if you like, has sort of more structure than the Grover search problem, but less structure than Shor's period finding problem. Okay, so it's intermediate between the two. Okay, so this problem is called the collision problem. And the problem is, one way to say it is you're given, F as a two, which is a 2-to-1 function. Okay, so each output of F has exactly 2 pre-images. And you would like to find a collision, which means just any pair of inputs, x and y, where f of x equals f of y. All right, so you can stare at this. Who can find a collision? I bet you can. Okay, yeah, so here's one. There's a bunch of others. Okay, so if I only have numbers from 1 to 11, it's not that hard. If the numbers range from 1 to to 10 to the 1,000, then it would be harder. Okay, so okay, a variant of the problem is that you're promised that f is either a 2-to-1 function or a 1-to-1 function, and you want to decide which. Okay, certainly if you could solve this search problem, then you could also solve this decision problem. Okay, and so I'll mostly sort of talk about the two interchangeably. Okay, so why did we care about this problem? Well, so sort of the original motivation, I think, was that this problem very closely models sort of a central task in cryptanalysis, which is breaking what are called collision-resistant hash functions. Okay, so in modern cryptography, you have these hash functions that compute a hash of a given message. Okay, and the security of the whole scheme depends on the assumption that it's computationally intractable to find 2 different messages that have the same hash. Okay, and you may have read in the news that sometimes people do manage to find collisions in these hash functions, and so then they have to upgrade it by usually by just doubling the key size or something like that. Okay, so this is a reason why some people might be interested in the collision problem. Okay, we'll discuss a bunch of other reasons later. So you've probably heard of the birthday paradox, which is, the reason why there's an excellent chance that there's two people in this room with the same birthday, for example. I'm not going to go through and do it, but okay, if there's, n days in the year, right, then in order to have a good chance of finding two people with the same birthday, you only need to gather about square root of n people, right, because what matters is the number of pairs. Okay, and so, you can use the same idea, and, in fact, in cryptanalysis, there's what's known as the birthday attack, okay, on hash functions, right, which is that you just pick a bunch of values of x, compute f of x for each one, and then you cache them, right, and you just look for, each time you get a new value, you look for a collision with any of the previous values. Okay, and if you do this, then you only need to look at about, square root of at about square root of n values of f before, with high probability, you're going to find a collision if f is a 2-to-1 function. Okay, but it's easy to see that classically this is the best you can possibly do. Okay, if f is a black box, then you really do need square root of n queries to, even probabilistically, okay, to find collisions with high probability. All right, so what about in the quantum case? All right, well here, quite, early, 1997, Broussard, Hoyer, and Tapp sort of noticed a very clever way that you can actually combine sort of the square root speed up of the classical birthday attack with the completely different square root speed up of Grover's algorithm, and so you get a quantum algorithm for finding collisions with cube root of n time. Okay, go figure, right? But it's, how it works is really simple. All you have to do is sort of first, classically, you're going to query like cube root of n values of your function. Okay, and then you're just going to cache them for fast lookup, or just, sort of store them, sort them, whatever. Okay, and then you're going to run Grover's algorithm on another n to the 2/3 values of your function. Okay, and for each of these, you're going to count each of these items. You're going to count it as marked if and only if it is equal to one of the cube root of n values that you queried classically. Okay, so you've sorted these. So this is a quick comparison to do, for each one of these. Okay, and so so the total running time of the algorithm is going to be cube root of n for this classical pre-processing step, and then for this Grover step, you need you need square root of n to the 2/3 time, so it's again cube root of n time. Okay, so the total running time is cube root of n. Okay, and yet by running for cube root of n time, you get to do n comparisons, right? Cube root of n times n to the 2/3. So if the function's 2-to-1, then with high probability you're going to see a collision, right? So it's like you're trading off two things, in some sense. Okay, and you get a cube root of n quantum algorithm for the collision problem in this kind of clever way. Okay, so then but then the question arises, well, is that the best you can do? Okay, and you could say, could there even be a quantum algorithm for the collision problem that made only one query or two queries, right? And that sounds kind of ridiculous, but and yet, in some sense, it's almost true. Okay, so, here's what you could imagine doing, right? So, just follow the paradigm of any of the sort of the famous quantum algorithms, like Shor's algorithm, Simon's algorithm, okay, where you would go into a superposition over all the possible inputs, okay, and then in superposition, you would query the function f, so you would get a state like this, superposition over x, f of x. And then let's say that you measure just the f of x register, okay, where again, f is a 2-to-1 function, and our goal is to find a collision pair for f. Okay, so let's see what happens if we measure the f of x register. Well, what will be left, just ignore this part, what will be left over in the first register will just be an equal superposition over the two different inputs that could have led to the output that we measured. Right, so we'll get an equal x plus y over square root of 2, where f of x equals f of y. All right, so it's like we've got the answer, really in our hands virtually, right? If we could just measure this state twice, we'd be done. Okay, just measure it, to somehow get out both x and y. Okay, then we would have our collision. Okay, so So, We just, and of course, like with Simon's algorithm, you do get to measure it in a way where you learn something about both x and y, but there you use that there's some additional structure in the problem. Okay, and here we don't have that additional structure. Okay, and the question is, can you still, by measuring in some clever way, can you get something out about both x and y? Okay, if you only got one of the two, then that's pretty useless because then, you're just getting a random input, which you could have, you could have just thrown away your quantum computer and picked one yourself. Okay, so, in some sense, we're, unlike with Grover's problem, we're not looking for a needle in a haystack here, just for two identical pieces of hay. Okay, so, and related to that, you could observe that sort of every one-to-one function differs from every two-to-one function on at least n over 2 of the inputs. Okay, so they really do differ globally from each other, right? And this is why you cannot use, for example, the optimality of Grover's algorithm, or any of the other sort of quote-unquote standard lower bounds to argue, for, the hardness of the collision problem, right? If this is really hard for a quantum computer, then, it requires sort of a new sort of argument. You can't just say that there's only this one collision in this tiny byte, because there isn't. There's collisions all over the place. Okay, so how do you argue that a quantum computer will have a hard time finding just one of them? Okay, so, this is something that, I worked on for about 4 months. I had, several dozen completely wrong ideas about, how to solve it. And, what eventually worked, was kind of not, what I would have expected at all. But it was this polynomial method, okay, which had been, proposed earlier by Beals, Berman, Cleve, Mosca, and de Wolf. Okay, and this was, a really striking method where you take, what you do is, if you want to rule out, let's say that there's a quantum algorithm for some problem that makes, a small number of queries. Okay, then what you do is you say, well, if such a quantum algorithm existed, right, that made only a few queries, then there would also be like a low degree real polynomial that would have to have certain properties. Okay, so it would represent somehow the acceptance, the probability that the quantum algorithm outputs yes, on various types of inputs. Okay, and so because it represents a probability, it has to be sort of close to, between 0 and 1, sort of at all the integer valued points, from 0 up to some large number. And also, because it has to solve your problem, it has to have a sharp jump somewhere. Okay, so you get, so each property that your quantum algorithm has to satisfy sort of translates somehow into some property of this real polynomial. Okay, but then the magic is that you can use results from approximation theory from actually the late 19th century, okay, to say that any polynomial that satisfies that list of properties must have a large degree. Okay, and then from that, you deduce that your original quantum algorithm must have made a large number of queries to F. Okay, otherwise it would have given rise to just an impossible polynomial. Okay, so it's a very sort of hands-off kind of method, right? It's you only use quantum sort of you only invoke quantum at the very first step, right? And the whole rest of the proof is really arguing about the properties of these polynomials. So it's a method that's very congenial to computer scientists, right? Or
This method also applied to classical.
Yes, in fact, it was introduced by Nissan and Szegedy, right, in '94, right, for various classical purposes. But I think it really comes into its own within quantum computing because, classically, usually there's all sorts of other things you can do besides using polynomials, right? But in the quantum case, there are cases where the only way we know how to do it is using this polynomial method. Okay. So, all right, so how can we apply this to the collision problem? So, all right, so we define these indicator variables. So let's say delta of x comma h will just be 1 if f of x equals h, and 0 otherwise. Okay, and then there's sort of a crucial lemma that one can prove is that, suppose you have a quantum algorithm that makes t queries to the function f. And then you look at the probability that that algorithm outputs yes. So call that P of f. okay, then you can show that P of f will be a polynomial in these indicator variables of degree at most 2t. Okay, so, and the reason why this is true is basically that, you know, if you look at the amplitudes, then the amplitudes will just be degree t polynomials, okay, because each time you make a query, that sort of increases the degree by 1, right? You can think of a query as a sort of, you know, multiplying by these indicator variables, right? Multiplying the amplitudes by these indicator variables, okay? And you know, in between two queries, you may make a unitary transformation, but that's just a linear transformation, so that doesn't increase the degree, right? So at the end, you have these degree t polynomials for your amplitudes, and then of course you have to square them to get probabilities, so that gives you degree 2t polynomials. Okay. So now what you do is, you know, we'll let q of k be the expectation of p of f over all possible k to 1 functions f. Okay, so first of all, a weird thing that we're doing is that even though the problem only asked to distinguish 1-to-1 versus 2-to-1 functions, we're now going to think about 3-to-1 functions, 4-to-1 functions, you know, 5-to-1, and so forth. Okay, yeah, and on those, you know, we don't know what the algorithm is going to do, but we do know that it's going to do something, and that its probability of acceptance will be between 0 and 1. Okay, that turns out to be a surprisingly powerful constraint. Okay, you know, it's a probability. Okay, so we're just going to look at the, you know, the probability that the algorithm accepts when given a random k to 1 function as input. Okay, and that we call q of k. Okay, and now, you know, since this is Jerusalem, you know, a miracle should happen at some point. Okay, so by the way, does anyone know what is the biblical unit of length called? What? But what's it called in English? Yeah, it's called the cubit. Yes, that's correct. So, okay. But anyway, the miracle here is that this q of k itself turns out to be a polynomial in the parameter k, okay, of the same degree at most twice the number of queries made by the algorithm. Okay, now why? Why should this q also be a polynomial? Okay, well, basically this is why. So I wish that I had an intuitive explanation. After 12 years, I'm not sure that I do. You calculate this q of k. It's a combinatorial thing, and there's all sorts of terms that could prevent it from being a polynomial, but those terms are in both the numerator and the denominator. So you cross them off, and you get a polynomial. And we've seen this happen sort of again and again with, this polynomial method. That sort of you get a univariate polynomial even in situations where sort of, it looks like a miraculous coincidence. And so now I just sort of expect it to happen. Okay, now there's a big, this is sort of the idea. There's a big technicality, which is, well, I said that k could be an arbitrary integer, right? But what if k doesn't divide n? Okay, then what do you even mean by a k to 1 function? Okay, so you have to give some more complicated argument that, deals with, the situation where k doesn't divide n, and that becomes more and more serious of an issue as k gets larger. And this is actually the reason why, the way of dealing with this issue is actually what sets quantitatively what kind of lower bound you're able to prove. Okay, so the original way that I had of dealing with this divisibility issue led to a quantum lower bound for the collision problem of n to the 1/5. Okay, I showed that any quantum algorithm, for the collision problem would have to give rise to a real polynomial whose degree was at least, n to the 1/5 power. So then, you'd have to make this number of queries. So all right, so at least, this was the first lower bound, which is better than one query. Okay, so that's, that's good, but, of course, that still doesn't match the cube root of n upper bound or algorithm that I showed you before. Okay, but fortunately there were soon some improvements. So Yao and Shi improved it to fourth root of n, and then a few weeks later to cube root of n, if the range of the function was much larger than n, and then Andras Ambayanis and Sandy Kooten removed the range restriction, so then we really got the right answer. We really know that cube root of n is the right answer for this problem. And once we knew that, then it actually gave us the right answer for another problem called element distinctness. Okay, so element distinctness is just, I give you a list of numbers, and, there's no promise that the list is 2 to 1 or anything like that. You just want to decide whether this list has any collisions at all. Okay, in this case, as you can see, there's exactly one collision in this list. Okay, and so the question is, what is the, how many quantum queries do you need to solve this problem? All right, well, so I claim that from the cube root of n lower bound for the collision problem, we can immediately deduce an n to the 2/3 lower bound for the element distinctness problem. Okay, why? It's cute if you've never seen it. Okay, well, suppose that there were a quantum algorithm for element distinctness that made less than n to the 2/3 queries. Okay, then let's say you want to solve, then I claim that we could solve the collision problem with less than cube root of n queries. Okay, how would we do it? I would just pick, a subset of my inputs for the collision problem of size square root of n. Okay, and then probably that if my function is 2 to 1, then that, by the birthday paradox, then that set probably has some collision. Right, so now I just run my element distinctness algorithm, but on that set of size square root of n, right? So the running time will be square root of n to the less than square root of n to the 2/3, which is less than cube root of n. Okay, but that would violate the collision lower bound that we already know. Okay, so we conclude that any quantum algorithm for this element distinctness also has to need at least n to the 2/3 steps. Okay, and that actually turns out to be optimal. Again, this was by a very, very striking quantum walk algorithm due to Andras Ambayanis, which once again was proved to be optimal before it was discovered to exist. But so now, we also know that n to the 2/3 is the right answer for element distinctness. Something about, there's some affinity between quantum and exponents that are multiples of a third. I've seen it again and again, but I don't know. Okay, so let me mention some other implications. You notice that sort of if we had a fast quantum algorithm for the collision problem, then among other things, we could very, very easily solve the graph isomorphism problem, in polynomial time. Okay, so what's graph isomorphism? It's I give you two graphs and I ask, are they isomorphic? Right? Can I rearrange one to be the same as the other? Okay, and so now suppose that we just look at this list. Okay, so this is a list of size 2 times n factorial, right? And it consists of, so if we have two graphs G and H, right? I look at all possible permutations, of G and all possible permutations of H. Okay, and suppose that I could find, let's say, random collisions, in this list of graphs. Okay, then if G and H are isomorphic, then probably a lot of those collisions are going to involve one graph over here and one over here, right? And in this way, by sort of finding collisions in the list, I could find, whether G and H are isomorphic. Okay, so the fact that there's not a fast quantum algorithm for collision finding, it doesn't tell us that there's not a fast quantum algorithm for graph isomorphism, but it tells us that if it does exist, then it's going to really have to use something more about the structure of this problem. Okay, it's going to either have to use the graph structure of the problem, or at least sort of the group structure, right? You're not going to do it in just this completely abstract way of just sort of looking for collisions. Okay, so right, so that's one thing. Another thing we learn about is quantum computing versus zero knowledge proofs. Okay, so computer scientists, as you may have heard, like to talk about these Arthurian legends where there's some all-powerful being who's trying to convince this king of something, and and often we would like our are proof to be zero knowledge, which means that Arthur should learn Arthur should learn that something is true, but he should learn nothing whatsoever about why it's true. Okay, so I claim that there is a zero knowledge protocol, a very easy one, for convincing someone that a function is 1-to-1 rather than 2-to-1. Okay, the protocol is simply the following: that Arthur could pick an input x at random, okay, and then he computes f of x, sends f of x to Merlin, and he asks Merlin, so what was x? Okay. So now, if f, the point is, if f is 2-to-1, then, Merlin is going to have to guess between two possible pre-images of f of x, right? And there's a 50% chance that he's going to guess wrong. Okay, and then, Arthur will see that he was lying. Okay, if Merlin can always pass that test, if he passes it 100 times, whatever, then Arthur can become statistically very, very confident that the function is really 1-to-1. Okay, even though he has no idea, he couldn't then convince anyone else, right? He doesn't have any sort of static proof of that fact. Okay, so we call this a statistical zero knowledge proof protocol. And so one thing that we conclude from the collision lower bound is that there are problems that have these fast statistical efficient SZK protocols, zero knowledge proof protocols, and yet which are not efficiently solvable by a quantum computer. Okay, or if you like, capital letters, which I know Eddie does. Okay, then there's we could say there exists an oracle relative to which SZK is not contained in BQP. Okay, that's another thing that we learn. So, okay, so another application, maybe the physicists would like more, concerns this index erasure problem. Okay, so let's say that we have some 1-to-1 function, say f. Okay, then it turns out that it would be useful for a huge number of quantum algorithms. Okay, if you could prepare just a superposition over all of the values of f of x, just a state like this. Okay, that would let you. It would let you do graph isomorphism. It would let you do all kinds of things. Okay, now it's easy to prepare a state like this. Okay, where you've got x and f of x. But then the hard part is, how do you get rid of x? How do you uncompute, or erase this x, which is garbage, and leave just these f of x's so that these guys can interfere with each other? Okay, so actually, you can kind of see how this might be related to collision lower bound, and in fact, by generalizing the collision lower bound, I managed to show in my original paper that any quantum algorithm to prepare this state has to make at least n to the 1/7 queries. Okay, don't ask where that comes from. Okay, but so at least there's not going to be you can't do it with log n queries or with one query or whatever. Okay, then Mitrojanis improved that to about n to the 1/5, and then recently Ambayanis et al. Gave a completely different, much more complicated argument involving representation theory, where they finally managed to show sort of the right answer for index erasure, which is that you need square root of n queries. Okay, that in order to I was arguing basically that if you could do index erasure, then you could solve something like the collision problem, and so you need a lot of since you need a lot of queries for that, then you do for this. Okay, but Ambayanis et al. Just sort of directly argued, about index erasure, and we're able to show that actually the best thing you can do, in some sense, is that in superposition you can, for each f of x, you can do a Grover search for the x, that corresponds to that f of x, and then once you find it, then you can erase it. Okay, but there's sort of nothing smarter than that you can do for this problem.
Does that give an alternate proof
Of the collision lower bound? No, it doesn't, which is interesting. It only gives a bound for index erasure, which is a very curious situation. That's one of my open problems, by the way. But yeah. Okay, so one of the applications that motivated me had to do with hidden variable theories. So I made an observation, which is that if you take a theory like Bohmian mechanics, let's say, where like you say that in addition to the quantum state, there's certain like observables, like the positions of particles in space that have real values, at any point in time. Okay, and you give some evolution rule, by which these sort of real particle positions change in time. Okay, then okay, in some sense, by construction, all of these theories are just empirically completely equivalent to quantum mechanics, right? So you may say, then it's obvious that they give you exactly the same power as a standard quantum computer would give you, right? No more and no less. Okay, however, you can, once you have like a hidden variable theory, you can then ask a different question, which is, well, how hard is it to actually calculate the entire trajectory of the hidden variable? Okay, so you don't, in a real system, you wouldn't get to see the whole trajectory, at any one time, right? But suppose you wanted to calculate like the whole hidden variable trajectory. Here's what they look like in the double slit experiment, for example. Okay, so I observed that if you could calculate this whole trajectory, then you could very easily solve the collision problem with only like one query. Okay, how would you do it? Basically, you would prepare this state, and then the key point is that if you could see the whole hidden variable trajectory, then you really could simulate the ability to measure the first register twice. Okay, because you could have your hidden variable either at x or at y, and now you just have to sort of juggle the variable around a little bit, sort of make it forget whether it was at x or at y. For example, by Hadamarding a whole bunch of the qubits and then Hadamarding them again. Okay, and get the hidden variable to sort of jump from x to y or from y to x. Okay, and if it, provided it does that, which it will do, much of the time, then if you look at the whole trajectory of the hidden variable, then with high probability you're going to see both x and y, and so then you'll have found your collision. Okay, so one conclusion is that not even a quantum computer could efficiently sample hidden variable trajectories. At least in this black box world. Okay, the way that I like to put it is that if at the moment of your death your whole life history flashed before you in an instant, and if during your life you had arranged a suitable interference experiment with your own brain, and if this hidden variable theory was true, then you could solve the collision problem in O of 1 queries, okay? And then you could do graph isomorphism and all these other things, okay? But there's no further assumptions than that, okay? So, and what's interesting about this to me is that this, actually, a hidden variable quantum computer could also do Grover search in cube root of n steps instead of square root of n. However, one can prove that this is optimal, even in the hidden variable case. Okay, so this gives essentially the only example that I know of sort of a model of computation that's motivated for some definition of motivated, and it sort of generalizes what you can do with a standard quantum computer, but only by a little bit. Okay, it's very easy to generalize quantum computers by a huge amount, so that you could solve NP-complete problems or whatever, right? Just add a nonlinear term to the Schrodinger equation, right? And that will do that. Okay, but to generalize quantum computing, but only by a little, is somehow harder. Okay. So now I'd like to mention some more recent applications of the collision Willer bound that sort of only emerged within the last few years. Okay.
This will also include graph isomorphism.
What?
It will allow you to do graph isomorphism.
The hidden variable model, yes.
It's a nice enlargement.
Yeah, exactly. It lets you do graph isomorphism, the approximate shortest vector problem. In fact, I proved that it does let you do all of this class SZK. So, it lets you do all of statistical zero knowledge. Yeah, but relative to an oracle, not the NP-complete problems. Right. Okay. So all right. So let me discuss a recent application. So there's a question about pseudo-random functions. Okay. So you may have heard that Goldwasser and Macaulay just won the Turing Award this year. And one of the many things that that sort of they won it for was this GGM construction. Okay, which is a famous way that you can start with a pseudo-random generator that sort of takes a random string, say of n bits, and stretches it to sort of n plus 1 random looking bits. And just from that tiny amount of randomness expansion, you can get a pseudo-random function, okay, which is a function that sort of, has 2 to the n possible outputs, and yet the entire function should be indistinguishable from a random function of 2 to the n bits. Okay, and so, in order to get this, they had to give this sort of very clever recursive construction. And then, they had to argue, which is basically the way that all modern cryptography works, right? That, well, look, we don't know if someone can break our pseudo-random function, if they can distinguish it from a really random function. But if they could do that, then they could also distinguish the original pseudo-random generator from being random. Okay, so the pseudo-randomness of the one implies the pseudo-randomness of the other. Okay, so but I and others sort of noticed some years ago that there was actually a very interesting loophole in their security reduction, which is that it breaks down the argument that they gave breaks down completely in the presence of quantum adversaries. Okay, why is that? Well, because their whole argument was about considering a polynomial time adversary, trying to distinguish the function from random. Right. Okay. So then each step the adversary queries some value of the function. Right. F of x1, f of x2, f of x3, and now we can sort of create a sort of a simulator, right, that will sort of, simulate, these values and show if you could distinguish these values from random, then I'll give you an algorithm that would also distinguish your original pseudo-random generator from random. Okay? But a quantum algorithm need not work in that way at all. It could, in a single step, just query, all of the values of f in superposition. Right? And so, the construction might still be secure, but it's clear that you're going to need a completely different argument to prove it. Okay, so, I gave this as one of my favorite open problems, and, just a year ago it was solved in sort of a remarkable work by Mark Zandri, who is a student at Stanford. And so he gave like a new security proof, and and I looked at his, he gave a talk about it, and I saw like there's all this complicated stuff, but then at the end there's all this reasoning about polynomials, and I'm like, Mark, this looks a hell of a lot like the collision lower bound, and and in fact, we subsequently figured out that you can just use the collision lower bound, as a black box. As just sort of one step of his argument. Basically, you argue that if you had a fast quantum algorithm to distinguish f from a random function, then you could either use it to break the underlying pseudo-random generator, or if not, then you could use it to break the collision lower bound. Okay, so that's basically what's under the hood of this result. Okay, now for my sort of this is what I was saving up to tell you. Okay, the relation of the collision lower bound to the black hole firewalls paradox. Okay, so this is a black hole. It's apparently it has to be an old black hole, one that's radiated away at least half of its Hawking radiation. Okay, and so outside of the black hole, there's some faraway Hawking radiation, which if you believe in the modern conjectures, to sort of somehow encode the information about the stuff that fell into the hole. Although we'd need a ADS-CFT or something even more advanced to tell us exactly how this happens. And then in between the sort of black hole interior and the faraway Hawking radiation, there's these near horizon modes. Okay, so this stuff that's sort of very close to the horizon. And so now some of you may have heard about this AMPS paradox, right? This firewall paradox that's sort of excited a lot of people lately. Okay, and basically the paradox is that you can give. So suppose that Alice is sort of throwing herself into the black hole. Okay, she's just really, really curious about this, about this particular issue. Okay, and then you can give physics arguments why these sort of certain qubits that are in this region H should be almost maximally entangled with the faraway Hawking radiation. At least from the standpoint of someone while they're outside of the black hole. Okay, but now when as Alice goes into the black hole, you can also give what look like very good physics arguments why these qubits in H should be almost maximally entangled with degrees of freedom that are inside of the black hole. Okay, but this is a problem. This would violate the monogamy of entanglement. Okay, the same qubits, would have to be entangled with two completely different things. And so then, the original paper suggested sort of a drastic solution, which is that, maybe, Alice can just never fall into the black hole at all. She just burns up when she hits the event horizon. Okay, so that's what they mean by firewall. What?
How Alice entered this argument? Or what is the role of Alice in this argument?
What's the role of Alice in any, in any argument, right? You could always just make her A. Okay, let her be A.
But why couldn't you argue it directly about the qubits?
Oh, okay. Well, so when people flesh out this argument further, as we're going to see, what they like to discuss is how would you actually reveal that there's a problem here? How would you actually reveal that there's entanglement here and that there's entanglement here? So they talk about the experiments that Alice would have to do, and they also talk about a second observer, Bob, who's outside of the event horizon. And they talk about, the reason why, there's a problem is that Bob's perspective says that there's entanglement here, but it should be reconciled with Alice's perspective as she goes in. Anyway, that's the... okay, but now, just this year, Harlow and Hayden gave, a very striking argument that, that says that look, yes, there's a problem here, but, in order to sort of actually reveal the problem, or sort of, see this violation of monogamy of entanglement, Alice would have to perform a decoding task that would require exponential time. Okay, so, complexity theory may come to the rescue of quantum field theory, at least if you believe this solution. So, they give an abstraction of Alice's computational problem, which is,
Why is the solution the exponential time?
Well, you can argue about it, but you can say, look, if there's some issue where like our normal notions of locality, of space-time have to break down in some way, but it's only going to happen after exponential time. Then you could say...
Your argument applied even if there's only single qubit. What is the asymptotic about the initial argument?
It's it has to do with the size of first of all, a black hole is not, it has to be sort of an old black hole that's sort of radiated. I mean, maybe the situation would be completely different for really tiny microscopic black holes if they exist. I mean, maybe Patrick can speak to that.
Well, it has to be a large black hole.
Okay, thank you.
But the
Yes.
connection to exponential time is just that the black hole evaporates away.
No.
So
Yeah.
if the black hole no longer exists by the time the decoding has been done, then
Yeah.
you can't verify it.
Yeah.
If you have a violation of monogamy,
Yeah.
how do you connect that to the amount of time it
Right.
requires to
Well, so that's exactly the objection that people have raised to their, to their answer, right? But I think that, what they say in the paper, which I agree with, is that, certainly what they're doing doesn't completely solve the problem, because you would need, some other, what you really want to know is sort of what is the right Hilbert space to really describe what's happening, right? And they're not even trying to tell you that. Okay, and so you really want some sort of quantum theory of gravity that would tell you, really, the issue is that, your notion of locality breaks down, and what you consider the inside of the black hole is really, not, you don't have to see it as the inside at all, right? But what they want to do is sort of tell a story that sort of at least makes you feel better about the situation, right? That without telling you what this theory is, that says that, look, at least the need for this theory is not going to, be revealed by only doing sort of simple experiments like the ones that we know how to do.
And going back a little bit, so
Yeah.
Just to understand the problem itself.
Mhm.
So how do you, for monogamy to be a problem,
Yeah.
the number of degrees of freedom there would have to be bounded, right? So if the Hilbert space was large enough, monogamy would not, you could have some degrees of freedom entangled without.
Yeah, that's right. But it's basically the same degrees of freedom, in order because there has to be like the dimension of the yeah, of the h degrees of freedom is much smaller than the dimension of either the inner, or the outer degrees of freedom, right? But it has to be sort of nearly, at least if you believe these physics arguments, they say that it should be nearly maximally entangled with both of them. Okay. So, all right, so anyway, so they sort of abstract Alice's computational problem as one of purifying entanglement, right? She wants to sort of reveal that this entanglement is really there. And so, so she's given sort of an n-qubit state, sort of on these three registers, B, H, and R, and we'll assume that she knows exactly how it was prepared. So she knows all of the physics governing the formation of the black hole, everything that fell into it, everything that came out of it. Okay, but now Alice only has access to the Hawking radiation. Okay, so she only has access to R. So the problem is, by acting only on R, is it possible for her to sort of distill EPR pairs between R and B, the black hole interior, and thereby sort of reveal that they were entangled? Okay, but then, Harlow and Hayden point out that this is a known complete problem for QSZK, for quantum statistical zero knowledge. Okay, and QSZK, we don't think is very likely to be in BQP. Well, why not? Well, because we don't even think that SZK is in BQP. Why not? Because of the collision lower bound. So it was, it was really, striking for me to read this paper, and strings and brains are flying all over the place, and I really, am struggling to understand. But then it gets to a point where, like, hey, I know that part. But okay. So all right. So I'm running out of time, but.
Why is this the abstraction of the problem? Why
Yes.
does it need to distill the
Well, she wants to, actually see that there is entanglement there, right? She can definitely see the entanglement between H and R, right? I think, sorry, between H and B, right? She can, that she can easily measure. And so then if she can see the entanglement between the other two, then she'll sort of explicitly violate quantum mechanics, right? By seeing that these same qubits are entangled with two different things. So that was their abstraction of, of the task. If you don't like it, then you should take it up with them. But so, all right. So just to, give a whirlwind, sort of, what other progress has been made. So Andras Ambayanis and I managed to generalize the collision lower bound so that it works for arbitrary symmetric problems. Okay, by symmetric I mean that you can permute the input numbers or the output numbers however you like, and and nothing really changes. So collision, element distinctness, Grover search are all examples of symmetric problems. Whereas, let's say, the Simon and the Shor problems are not, because if you permute things, then you destroy the periodic structure. Okay, so John Watrous conjectured a decade ago that for any symmetric problem, there should not be a super polynomial quantum speedup. Okay, or maybe only a Grover type speedup. Okay, and we managed to basically prove that. We've shown that for any symmetric problem, the randomized query complexity is at most the quantum query complexity to the 9th power. It should be the 2nd power, but there's a polynomial relation. Okay, if you only have one symmetry and not the other, then this is still an open problem. So I also recently managed to show that there are no short quantum proofs that a function is collision-free. So let's say you want a small quantum state that certifies that your function is 1-to-1 rather than 2-to-1. And then you want to verify that certificate with few quantum queries. I showed that you can't do that either. So you get an oracle where SZK is not in QMA, if you cared about that question. Okay. So I have a program that I'm trying to do today with a student, which would try to get a separation between quantum and classical proofs, which is a big problem that Umesh mentioned in his talk. Okay, to show that really, for some black box problem, a quantum proof can really be exponentially more efficient than any possible classical proof. Okay, we have a candidate for that. I don't have time to go through it, but the candidate is something called the separate components problem, which was introduced by Andy Ludomirsky, and it's very easy to see that this problem is in QMA. Okay, but we strongly conjecture that this problem should not have a short classical proof, even one that you can verify quantumly. However, in order to prove that, you're going to, this problem reduces to the index erasure problem. Okay, so any lower bound for this problem will have to generalize the lower bound for index erasure. And so, I think that it's going to take a pretty far-reaching generalization of the collision lower bound, in order to solve this. And we have some partial progress, but there's a ways to go. So, one of my favorite open problems still today is a quantum time-space trade-off. Can you show that in this cube root of n algorithm for collision that you really needed a lot of qubits? That if you had only few qubits, then you would need, say, square root of n queries. Okay? Right now, we have sort of no techniques for proving that sort of time-space trade-off. That was the situation 12 years ago. That remains the situation today. And then Umesh already mentioned, another of my favorite problems, which is we have, besides the polynomial method, the, other even sort of, much more broadly applicable method that we have for, ruling out quantum black box algorithms is Ambayanas's quantum adversary method. Okay, and just recently, Belov's managed to prove the element distinctness lower bound using the adversary method. Okay, we also know, in principle, that it must be possible to prove the collision lower bound using the adversary method, because there's this great result of Reichardt that says that the adversary method is always optimal, right? It always, it can prove any lower bound. Okay, but right now, the only way that I know how to prove the collision lower bound with the adversary method is to say, well, look, take the polynomial method proof that we already have and then sort of put it over, right? We know that because of that there has to be this other proof, right? Can you really explicitly give an adversary proof of the collision lower bound? This remains something that no one knows how to do. So, concluding thoughts. So there's sort of a hierarchy of structure here, from abelian group problems, say, to non-abelian group problems, to the collision problem, to the Grover search problem. Okay, as you have less and less structure as you're going up. Now we know that you get an exponential quantum speedup for the abelian group problems, and for a few non-abelian ones. We also know that for Grover and for the collision problem, you get no exponential quantum speedup. But only a polynomial speed up. So, each advance that we've made in figuring out which types of structure quantum computers can and can't exploit, has led to, I think, to unexpected conceptual lessons, about, computing, about physics. And so, unlike for the sort of the geezers like me, but, for the young people here, I think that there's lots and lots of open problems that beckon. So I'll stop there. Thanks. Yeah.
And also, I understand your solution about the black hole.
Yeah.
If we wait enough time, then also the intense. If we wait enough time, also the internal degrees of freedom will eventually go out.
Mm-hmm.
Then we can ask the question: once everything is out, what is the entanglement between the degrees of freedom that were in the boundary and they are out? The degrees of freedom were interiorly out, and the other, then we claim there is a problem there, because there is entanglement with those degrees of freedom, and there is entanglement with those degrees of freedom. Now in principle we have infinite amount of time to check.
Yeah, that's right. So Patrick can probably say more, but my understanding of the situation is that, the current sort of conjectures that the quantum gravity people believe, lead them to expect that if you always stay out of the black hole, then there's really no paradox here, right? Then everything is perfectly unitary, okay? So all you're going to see is that the black hole evaporates, and it's sort of no different than, in principle, than like a piece of wood burning or something, right? You'll see some complicated unitary process, and the information will emerge, right?
No,
the only
that you're talking about a constant black hole, but suppose the black hole disappears completely.
Yeah, no, I'm saying after it, even as it radiates away, even entirely, that the whole thing can be described completely unitarily by someone who is outside, who remains outside the event horizon, right? At least this is the picture that the ADS-CFT leads you to.
The event horizon disappeared. after.
Yeah, but you know the issue is that you know like your Hilbert space, right? As it's radiating away, it sort of goes right up to the boundary of the event horizon and not into it, right? And then your space, I guess, gets bigger as the event horizon shrinks. Okay, but your Hilbert's
Either you say there is a singularity left, or the whole thing that was inside now is outside.
Well, okay, so these are like deep quantum gravity issues that I'm not qualified to get into, but I think at least what the string theorists believe today is that the whole thing will evaporate away, and that the whole thing will look completely unitary to someone who's outside the event horizon. The issue that they worry about is that for someone who's falling into the black hole, there seems to be no single Hilbert space by which you can describe everything that's going on, both outside of the hole and inside of the hole. Again, you have to take it up with them if you have further.
That doesn't make sense because once if you wait enough time that the whole black hole disappears, there is no meaning anymore to distinguish between the degrees of freedom that were inside and the degrees of freedom that were outside. They are all now outside.
Well, in some sense, from the perspective of someone who's outside the hole, like nothing ever falls into it, right? You never see anything fall in. Everything just stays on the horizon. Yeah.
So I think within this model, the idea is that once the black hole evaporates completely, the internal modes are gone. So they never get out. But that doesn't cause information loss because when things fall in, the information gets replicated in the outside modes and the inside modes.
Right. That's what I was trying to say. Thank you.
Further questions?
One very naive question.
Yeah.
But how much of the when we talk about these problems, we always compare to what you can do classical, what you can do quantum mechanically. But we have only a limited amount of classical resources for all practical purposes. And as far as I see there, one always assumes to have an infinite amount of classical resources.
No, that's not the case at all. You're always comparing the best classical algorithm against the best quantum algorithm, and you're trying to see how much speed up do you get. That's exactly the question here.
Yeah, but
so,
can you, does it imply that your classical algorithm can have an infinite amount of time and an infinite amount of bits?
Well, okay. So first of all, in the black box model, you don't limit the number of you don't limit the amount of memory. The only resource that you're interested in here is the number of queries that you make to this black box. Okay, this is your model that sort of it captures a lot a part of what you're interested in. Of course, not all of it, right? Of course, it doesn't touch the P versus NP question, or when you start looking at the internal structure of your function. Okay, but in both the and I mentioned as one of my big open problems to try to get trade-offs between the number of queries to F and the the number of qubits that you would need, the amount of memory that you would have, right? But but what you do in this model is in both the classical and the quantum cases, you look at how many queries to F are needed, right? Just assume for simplicity that that all the other resources are unlimited, right? Because in many of the situations, in many of the actual algorithms that we know, the number of queries to F sort of is the limiting resource. Right, that is what's causing you to need exponential time, right? And so just try to understand that, right? And if even the number of queries to F is exponential, then certainly the number of computation steps is going to be exponential, right? So so in some sense, like I don't have to worry about what you're saying if I'm proving lower bounds. If I'm designing algorithms, then sure I have to worry about it. Yeah.
If I may just continue Yakir's question, perhaps with you and
yeah.
So, is it a point that essentially you say there remains a remnant, only that the remnant is not entangled with the rest?
No.
Or could you map into that?
There might be no remnant.
Okay, they disappear, but could you also map this into the idea that there is a remnant as far as mass is concerned or something, only that it becomes fully disentangled from what it evaporated?
That's possible.
You mentioned some exponential quantum speed up for some non-abelian group.
Yeah.
Can you mention some interesting example
yeah, that there's
of
not
some groups?
Well, I can mention some uninteresting examples.
Only non-interesting.
No, there's not. So there's very few. Right? But there's this non-abelian hidden subgroup problem that you might know people sort of bang their heads against for 15 years, and mostly they manage to prove negative results. Saying the various approaches don't work. Okay, for some very special non-abelian groups, I think like the Heisenberg group, and a few others. Okay, they managed to design basically managed to sort of use the abelian-like, the Shor-like quantum algorithms and say that, they still work if your group is just a little bit non-abelian. Okay.
Are there applications in cryptography like homomorphic
well, if we could push it further, then there would be. So if you could solve this non-abelian hidden subgroup problem for the dihedral group, for example, then you could break lattice-based cryptography. Okay, and for that reason, that's a goal that a lot of people have been thinking about. But we don't yet have a quantum algorithm that does that. That's why I just drew this line. It's just going up a little tiny bit into this non-abelian block.
Okay, thanks.
Okay. Yep. Okay. Yeah, good to see you. Good to see you too. Yeah, so I'm sorry that I don't
לעשות תמונות של כל באי הכנס, יש איזה מקום שעושים. מתי? לא. מתי? עכשיו? לא, לא עכשיו, כי לא הודענו לאנשים. אולי בהפסקת קפה הבאה שתהיה, את הצהריים. מתי אתה נמצא? מתי זה הפסקת קפה? שעה? בערך ב-4, אני צריך להסתכל בתוכנית. בסדר, תדאג לרכז את כולם. איפה? כמה אתם? כל מי שפה. 180? אז תעמיד את כולם בכניסה לבניין. יש איפה שהכיתוב במכון לימודים מתקדמים. קיר השחור, עם הגב לקיר. כמה שורות. אפשר להעמיד אותם? יש מספיק מקום. צילמנו שם בית ספר לכלכלה עם פחות, אז עם יותר, אז אין בעיה.